Let's talk about molecular geometries, the shapes of molecules. This is really important because shape or structure determines function, especially as you get further along in chemistry and look at organic chemistry and biochemistry. So we're going to start with the Lewis structures, and we're going to first determine the number of electron domains. An electron domain is either going to be a non-bonding or lone pair. That's one type of electron domain. Another type of electron domain is a bond, be it a single bond, a double bond, or a triple bond. They're all equal one domain. And so let's look at carbon dioxide. This carbon is the central atom, and we're going to focus on the central atom in all of these examples to determine the molecular geometry of the shape. And so it has two double bonds. It has no non-bonding or lone pairs. It's got two bonding electron domains. So the total number of electron domains is 2. The hybridization, if it's 2, means that it's sp. If it's sp, it's going to be 180 degrees. By the type of molecule, I mean that it's got a central atom and 2 other atoms on it. So we're going to label this as AB2. So if it's 180 degrees in sp, the electron domain geometry is linear, and since there are no non-bonding or lone pairs in the central atom, the molecular geometry or shape will be the same. It's also linear. BH3 has 3 single bonds. Each one counts as a single electron domain, has no non-bonding pairs. So there's a total of 3 electron domains. Those 3 electron domains are trying to arrange themselves to maximize the distances between them, to maximize the angles between them, in order to minimize repulsive forces. We call that VSEPR, valence shell electron pair repulsion theory. So if it's the number of electron domains is 3, the hybridization is what we call sp2. The ideal bond angles are 120 degrees, and it's trigonal planar for both electron domain geometry and the molecular geometry. And this type of molecule we could have classified as being AB3, a central atom with 3 atoms around it. Even though the Lewis structure shows bond angles of 90 degrees, the Lewis structure does not have to exactly show what the bond angles are. And so don't let that throw you. The next one, SO2. Now we have one non-bonding or lone pair. We've got a pair of double bonds, each of which separately counts as electron domain. It means once again we have 3 electron domains in total. It means it's sp2. The ideal bond angle would be 120 degrees. This is actually going to be a little bit less than 120 degrees. That non-bonding pair takes some more room on the surface of that central atom, if you want to think of it that way. It's got a greater repulsive force. And so that bond angle may be like 116 degrees or so, but it's going to be less than 120 degrees. This type of atom I want to call AB2E. Central atom is A, it's got 2 atoms on it, or B, and it's got a non-bonding pair E. If it's sp2, the electron domain geometry is trigonal planar. When we look at the molecular geometry, we only look at the atoms involved. And so that non-bonding pair is really going to force those bonding pairs, those double bonds, away from it. It's going to bend the molecule. And this is going to be a type of molecular geometry that we're going to call bent. That was SO2. The next one is CH4 molecule we call methane. If we do the type of molecule it is, we got one central atom that has 4 atoms around it. So it's got the 4 atoms around it, so it's got 4 bonding pairs. Has no lone pairs or non-bonding pairs. That gives us a total electron domain of sp4. Gives us a total electron domain of 4. Hybridization is sp3. If it's sp3, the bond angles are not 90 degrees as shown, which is not a flat molecule. It actually occupies 3-dimensional space. So those bond angles are actually going to be 109.5 degrees. And that electron domain geometry we describe as being tetrahedral. Since there are no non-bonding pairs on the central atom, the electron domain geometry and the molecular geometry or shape are the same, tetrahedral. NH3, ammonia. It's a type of molecule that we call AB3E. There are 3 atoms about the central atom and 1 non-bonding pair. There's that one non-bonding pair. There are 3 electron domains. Gives us a total of 4. If it's 4, it's sp3. If it's sp3, the electron domain geometry is tetrahedral. When we look at the geometry or shape, we're just looking at the atoms involved. Even though there's a non-bonding pair on the central atom that does influence the shape, we don't include that in the shape. And so this winds up being trigonal pyramidal. Makes a pyramid. So this bond angle is going to be less than 109.5 degrees. And in ammonia, it's about 107 degrees. The next molecule is water. It's a type of molecule we could call AB2E2. 2 atoms on the central atom, 2 non-bonding pairs. Gives us a total number of electron domains is 4 once again. If it's 4, it's sp3. If it's sp3, it's tetrahedral for the electron domain geometry. A more accurate representation of the shape of the molecule, the Lewis structure is correct, is drawn. Because Lewis structures, as we said, don't have to show the correct bond angle. Once again, this is going to be a bent molecule. That bond angle is going to be less than 109.5 degrees. It's more like about 105 degrees. Next molecule, phosphorus pentachloride. We've got a central atom, phosphorus, with 5 atoms surrounding it. There are no non-bonding pairs on the central atom. There are 5 chlorines, 5 single bonds. Each single bond counts as a single electron domain. That gives us 5. And now we have a hybridization that we're going to call sp3d. sp3d. And this makes an electron domain geometry being a trigonal bipyramid, or it's trigonal bipyramidal. And since there are no non-bonding pairs on the central atom, the molecular geometry and electron domain geometry are the same. So it's also trigonal bipyramidal. If you haven't been looking at a book with some pictures of these, or actually looking at molecules, this is certainly the time you want to start doing this. Around that phosphorus, there are really 3 chlorines that all lie in a plane. We call those equatorial positions. And there are 3 chlorines on the axial positions. So there are 2 bond angles in here. There's a 90-degree bond angle between an axial and an equatorial position, and there's a 120-degree bond angle between the equatorial atoms. So there are actually two bond angles, 190 and 120 degrees. The next one, SF4, sulfur tetrafluoride. We have the central atom of sulfur. We got 4 fluorines, and this time we have a non-bonding or lone pair of electrons on the central sulfur. So we got 1 non-bonding pair, 4 atoms that are bound to the central atom, 4 single bonds. That gives us 4 bonding electron domains. Gives us a total 5. 5 means it has a hybridization of sp3d, which means it has an electron domain geometry of trigonal bipyramidal. The question is, where do you put the non-bonding or lone pair? Do you put it on an axial position or on an equatorial position? Put it on an axial position, that non-bonding pair of electrons has a 90-degree angle to the equatorial atoms. If you put it on an equatorial atom, it's got a 90-degree difference with the axial atoms. Now there's a 120-degree difference with the equatorial atoms. So it winds up being that the non-bonding or lone pair actually goes on an equatorial position and makes something called a seesaw shape. And so that bond angle's around the equatorial position is going to be less than 120 degrees, and it's going to be less than 90 degrees. It's going to cause a deformation along the axial positions also. I really encourage you to get out a book and look at a picture of this at this point.